Recording in progress. It's not to charge. But even you at least will go and look at the pictures.
Stop that. Stop that.
Video.
All right. You guys are able to see everything well? Okay, because I'm going to record this.
Yes, sir. We are able to see.
Okay, all right. Okay, so you can now go and look at some examples. Okay, I think let me just attend to your question that you asked. Yeah, so what basically say, according to this law of conservation of energy, we
You
say
guys,
energy in a
stop
system.
that. Stop that.
Guys, please mute your microphones. So I'm basically saying in a system, energy is neither created nor destroyed. Because when you create something, it means you are adding to what is already there. Not when you destroy something, which means you are removing from what is existing. So what I'm basically saying is that in a system, okay, the change in energy is available. The change of energies in a system is zero. implying that there is no change. It's just a conversion. If I convert 40 joules, I can change it from this state to that state to see the same joules, just as it's working in different what? States. Just like you ate shima with I don't know how much calories that you are burning. I mean, that shima now is the one that you're using to walk, to do all those things. We're just changing from chemical energy to mechanical until we do all kinds of kinetic, you run. So it's just a conversion, implying that the change in a system of energy is basically what? Zero. Okay, so now we are good to solve some problems on this part. So we see how questions come up. See how problems here come. Start with basic examples, then we build from those examples. Okay. That's where we go start. Okay, so I think this one. This. Okay, now let's start with this one. I think it's an example which I've given before, and it also comes mostly in physics tests from principles of physics. Just an example. 300 kg roller coaster starts, or roller coaster car starts compresses. Point A. As shown below. And goes down track. Retarding friction force 20 newtons. How fast is the car going? Okay, so this is a diagram. So that this problem in class, you can do it in system vision. Okay, so this is the diagram. try to look at it. So copy it, then we see what we need to do. Okay, remember this. There's a quiz. It's just an exercise. I've stopped using words like quiz. Puts people in blind mode. I'll just be saying exercise. Just the same, I mean, for the same thing. At the end, examples, exercise. Okay. So, by now. Okay. Okay, so you guys are done. I explained on this problem.
Yes, you can.
Okay, perfect. So what I'm simply saying right now is that we've got this interesting problem. Okay. So first we have to understand what is happening. Then we can know which theorem or which laws we can use. We know the principles which are applied, right? So now let's look at this question. Say a 300 kg roller coaster car starts from rest at point A. So this is why it's at point A. Now the key word here is rest, which means initial velocity is what? 0. So we take note of that, we bear that in our mind. As shown below, and begins to coast down the track, right? It's now going down the track. Okay. If the retarding friction force is 20 newtons. Now, when you hear the word retarding friction force, implying that what kind of energy is existing? Thermal energy, right? So thermal energy, when you do your hands like this, you feel the heat, right? Because of the friction which is existing, right? So because of the presence of friction force, you have what is called thermal energy. So thermal energy is a product of friction force over the distance. So we have to know the friction force and the what? The distance. That is what is thermal energy. Because remember, when done, the force times change in the displacement, right? So implying that this force is frictional force, and the displacement there is based on what we are. So thermal energy is existing because of the friction force. So bear that in mind. Now the question is asking you, how fast is the car going at point B? So now, this one, the way you can only solve this problem is using the law of conservation of energy, right? Why am I saying we should use the law of conservation of energy? Now, if you see here, we know that this is at point what? A. And at point A, we know that this orbit at a particular height, isn't it? Now we know potential energy is because of the height. So implying that, 10 meters high, this guy has the potential energy, right? Now the potential energy is converted into what? The potential energy is being converted into kinetic and friction. You see that? I didn't say it's changing, it's converted. You get the point? Because this guy is at rest. Then what is making it to slide? It is at rest. What energy does it have to make it slide? It has the potential energy, which is converted now to kinetic as well as what? Thermal energy because of the presence of what? Friction. So once we have written this, the next question is asking us how at point C as well, at that point. Okay, so I'll keep this diagram. I'll solve at the top there because I want to be using this diagram for analysis. Is that okay? So this is what we're going to do. Now, this topic, as I'm explaining, is very, very important. Also, linear momentum. Understand this part. Linear momentum, circular motion. We will have to understand it. So now, let's do. What is the formula we have? We know that there is no change in the system. There's no change of energy in the system, right? There's just what? Convection. You get it, right? Now, if you see here, look at the kinds of transitions of energies. Those are the ones that are supposed to appear in that equation. Is that okay? So we're seeing that there's potential energy to kinetic, then there's also what? Thermal. So implying that these three energies, they are all appearing in the law of conservation, the formula. Is that okay? So implying that when we're doing it now, we say solution. We're going to say this is basically a change in energy plus change in H plus. So then we normally just compute unless we have been given two states, I mean two positions from here to there, but most we just compute them. These are the things that appear in my analysis here also. Yeah, we have seen those transitions. But remember, when we say change, we're looking at an initial state and a particular final state according to our analysis, right? But at this stage, we're now looking at just at what? Isn't it? So we're looking at this flow from A to B, isn't it? On those positions. So, which means my analysis should just be centered, because I want to find the speed at this point, right? So my analysis should just be centered on this point. I compute whatever is happening here, isn't it? So whenever I see change, it's the difference between the initial state, which is NGH final minus NGH naught, difference between the initial state, the final state and the initial, plus H again, 1 over 2 N B final squared minus 1 over 2 N B squared plus this guy, because basically friction here is 0. You get the point, right? The initial one is 0, the distance is 0. You get the point. So basically, we just compute the actual one, which is just basically thermal energy is the product of friction force times the actual path the object takes. So we just put the rate, right? The actual path to give us what? Isn't it? Now, what you have seen is that my analysis, I was trying to interpret what is happening. You get it? Interpretation of what is happening. Now, this is the part where I've now started making my computations based on my analysis. So now, since I know that the initial velocity is equal to what? 0, right? H initial 10 meters. Not so. This is where the object is starting initially, to where the object will fall. Isn't it? So I can take, if this is the ground state, I can take my H final as equal to what? 0. Because you can see this is a ground state, not it can become 0. Then if that is the case, what else do I need to know? Okay. The L is basically the actual path the object uses from position A to B. You get it? The actual path, which is what? 40 meters. So my L is basically what? Now, I'm extracting this still based on my analysis. So now, I now come back to the computations and make substitutions for these values, isn't it? Right? Bear in mind, I need to find the velocity. But because of this analysis, the velocity that will remain is the one I'm supposed to find. You get it, right? So implying that my H final is going to be 0. So implying that this whole computation becomes 0. You get it? So it will be N. My H final is what? 0. What's that? Minus N G H naught. So for now, I already know the value of my H is 10, right? So I can just keep it because I know it's still existing. Okay. Anything that is 0, I want it to go. Plus 1 over 2. And I know my final velocity is the one I'm supposed to find right now because the initial is also 0. You get it, right? So implying that I'm going up d m squared minus 1 over 2 and b that is 0 plus f that. Okay, so now I wanted just to see why some computations were removing them. Is that okay? So what we're going to remain with, okay, for this one now, okay, start. Right, okay. What I'm remaining with right now is these guys here, so I'm going to have negative h naught plus 1 over 2 m v f squared, that is 0, plus f r f. Oh, let me just make my h final substitute for, isn't it? Then I can punch the values at the end, the remaining ones. It will be easier for me like that. Is that okay? Are you following? All right. So if I make these guys at the formula, I'm going to 1 over 2. And you guys, if it cuts, there's under a minute, you join again. So h squared is equal to the other side, mg h naught minus that. Then we take this gets 1 over 2 m 5 by 2 over n. So implying that I can take a root of this. You are seeing what I'm doing, right? You are seeing what I'm doing? This is just a reciprocal. If I want to cancel the